Okay, so here is going into section 7 problems. This is number 2, was to show that F and G here are bijections. So the thing to note, you've got to show 3 things. You've got to show they're well-defined, an injection and a surjection. So let's look at F first, and we can see that if for example, if we look at F of A minus B plus 1B, that's equal to AB. Okay, so this is to show its surjection, so we can get any element in A, right? So the set of points in Z plus cross Z plus such that that y is less than or equal to x, so we want B less than or equal to A. Since B is less than or equal to A, then A minus B plus 1 is going to be in Z plus. Okay, so that shows that F is a surjection and well defined. And then if F x1, let's do it, y1 equals F of x2, y2, then that means that x1 minus y1 minus 1 y1 equals x2 minus y2 minus 1 y2. And if that's the case, then y1 equals y2. And if then that's the case, x1 equals x2. So it is injective. And then working on G, working on G, it's well defined. The main thing to note there, it's well defined, is because when you've got x minus 1 times x divided by 2, if x is an integer, then that is also going to be an integer, because one of those has to be one of x minus 1 and x has to be even. So this map is well defined. And then the easiest way to show that G is a bijection is to construct a G inverse. And so the way that I did that was, okay, so if we have Z an element of Z plus, then let Z equal the ith triangular number minus J. So Ti is the smallest triangular number, which is greater than or equal to Z. And note that by the definition of triangle numbers, J has to be less than or equal to I. So Ti is a half I times I plus 1. That's the ith triangular number. Notice this triangular number must exist and be unique, because that formula, half x minus 1 times x, is monotonically increasing. So if we let G of I minus J, look what that equals, then that is equal to a half I I think I want this to be minus 1. So I think we want to look at I minus 1 right there. So we've got Ti times I minus 1 plus I minus J. And then that equals a half I plus 1 minus J. And so using that, we can define an inverse for G and show that it is indeed a bijection. Okay. Okay, for problem number 3, we want to show there's a bijective correspondence between the power set for the positive integers and the Cartesian product x omega, where x is 0, 1. Well, this is pretty straightforward. Let's sort of set up that bijection. So f, let's say, going from power set for z plus to x omega by defining f of a. So remember, a is some subset of integers. Well, we'll just let that be x1 of a, x2 of a, etc., where xi of a equals 1 if I is in A and it's 0 otherwise. Okay, and correspondingly we can define G from x omega to the power set of z plus by G of acting on an element from that product set to be a set of indices such that xi equals 1. And that, so both f and g are well-defined functions, and we can see that g of f of some space is going to be, subset is going to be A itself, and f of g of some element from that product space is going to be what you started with. So they're inverses of each other, so we have a bijection. Excellent. Okay, and then the final problem from section 7 was number 5, A and E. 5A, well, that is going to be countable. And why is that? Oops. Because we can get a function from A to z plus cross z plus by just defining it to be the double f0 f of 1. Okay, and the product of countable sets is countable. Whereas if we look at E, this is going to be uncountable because this is just the set x omega that we talked about earlier.